Okay, so if you're listening to this, you're probably the kind of person who really wants to understand, like, the nuts and bolts of what makes a glider perform well.
Yeah.
Right, and you don't want to have to wade through tons of technical documents or anything. So we're going to do our best here to break down these key factors that influence a glider's performance in flight.
Absolutely.
We've got some really insightful information here that we're going to use to guide us.
It is great stuff.
It is. Think of this as like a fast track
Yeah.
to really grasping, like, why some days it feels like you're soaring effortlessly, and other days it feels like you've got a piano tied to your tail.
Exactly. And you know, the fundamental thing here is how the design of the glider, which is fixed, obviously,
Right.
meets the realities of the atmosphere, the wind, and even the glider's own weight.
Yeah.
And it's that interplay that dictates, you know, every moment of the flight,
Right.
whether you realize it or not.
So our material kicks off by really highlighting this point that while the glider's design is certainly key, it's fixed once it leaves the factory, right?
Yeah.
It's those variable factors, things like density, altitude, wind, and weight, that change from flight to flight.
Right.
And these are really the three big players that we need to understand for any given, sortie.
I think one of the most interesting ones there is this idea of density altitude.
Yeah.
Because it's not just how high you are above the ground, it's really how high you feel like you're flying at.
Right, yeah.
So a higher density altitude means essentially that the air is less dense, or as our source puts it, thinner.
Okay.
And that has a real impact on how the glider performs.
I like to think about it almost like if you're trying to fly a kite on a very humid day
Yeah.
versus a very crisp, dry day. It just feels like that humid air is thicker, or, well, maybe not thicker, but less buoyant
Yeah, yeah.
for the type to fly in. And that's kind of like what high-density altitude is doing to a glider.
Yeah, absolutely. And our material details a few things that contribute to this thinner air.
Mhm.
You know, high elevation certainly plays a role, but low atmospheric pressure, high temperatures, and even humid air.
Okay.
All of that makes the air, less substantial, less supportive for the glider's wings.
Yeah, yeah.
And on the flip side, flying from a lower field elevation on a day with high atmospheric pressure and cool, dry air is going to give you lower density altitude, so the air is thicker.
Right.
And generally speaking, better performance.
Okay.
Now, here's something really important. You don't have to be in the mountains
Right.
to encounter high-density altitude. A scorching summer day at a relatively low-lying airfield can create the same effect. You know, that pre-flight consideration that they talk about in the material is really key here. It's vital.
So how do pilots actually go about figuring out this density altitude? The document mentions a chart, figure 5:1, and it walks through an example
Yeah.
where you've got a field elevation of 1,600 feet above sea level,
Okay.
altimeter setting of 29.80 inches of mercury,
Right.
and a temperature of 85 degrees Fahrenheit. It's a lot of numbers to juggle in your head before a flight.
It is. But the chart really helps simplify it.
Okay.
And so the first step in the example they give is you've got to account for this non-standard atmospheric pressure. So that altimeter setting you mentioned, that's the pressure that the pilot sets on their altimeter, that 29.8 inches of mercury is different from the standard.
Okay.
So they add 112 feet to the field elevation to get what they call the pressure altitude,
Right.
which in this case is 1,712 feet.
Okay.
Then you take that pressure altitude and the outside air temperature over to this chart.
Okay.
And where those lines intersect is your density altitude,
I see.
which in this example is roughly 3,500 feet.
So even though you're sitting there on the ground at 1,600 feet, the glider's going to perform as if it's at 3,500 feet.
Exactly.
On a standard day. Wow, that's a big difference.
It is, and it really underscores why understanding this is so important. Our source does point out that a lot of performance charts in the glider's manual will use pressure, altitude, and temperature directly,
Right.
which cuts out that last step. But knowing how to calculate or find density altitude using a chart or a flight computer, is a really valuable skill to have.
Okay. Moving on to atmospheric pressure itself, our information tells us it's not a constant. It changes day to day.
Right.
And these changes directly impact density altitude. It even gives us a METAR example, KDAL 232153Z, A2953. That A2953 is a pressure reading that's lower than standard.
Yeah, and it's interesting how even that, what seems like a small difference in atmospheric pressure,
Mm,
can really affect how your glider behaves. So lower pressure means higher density altitude.
right.
And as we talked about, that means decreased performance, longer takeoff runs, less impressive climb rates, and longer landing rolls,
Mm.
not just for the glider, but for the tow plane
Yeah,
too.
yeah.
Like the whole system's working harder in that thinner air.
Got it. And of course, the opposite is true. When atmospheric pressure is higher, you get lower density altitude and a nice little boost in performance.
Yeah, exactly. It all ties together.
Okay. Then there's temperature, which our source really emphasizes has a significant effect on density altitude.
Mm,
As that hot air expands,
it does.
becomes less dense.
Right. You can think of it as when the air heats up, the same number of air molecules are just spreading out to
Hmm.
fill a larger space.
Okay.
So that less dense air provides less lift for the wings and reduces the efficiency of the engine and propeller if you're flying a self-launcher.
Right, right.
So higher temperatures equals higher density altitude.
Hmm.
And that means all those performance penalties we talked about.
Yeah, that makes sense. The source gives a really interesting comparison between Love Field in Dallas and Denver International, KDEN.
Okay.
And it really illustrates this point.
Yeah.
Same altimeter setting and temperature on a hypothetical day, but vastly different elevations, 487 feet versus 5,431 feet.
Wow.
Yeah. So the resulting density altitudes were 1,774 feet for Dallas
Okay.
and a whopping 7,837 feet for Denver.
Oh, wow.
It really shows you how that physical altitude and temperature work together.
Mm-hmm.
Denver's already starting out with a higher density altitude because it's so high above sea level.
Right.
And then the temperature just adds this huge layer on top of it.
It's a really stark illustration of how even a small change in elevation combined with temperature can create really different conditions.
Right.
So always factor those two things in.
Okay, the next piece of the puzzle is wind.
Yeah.
And this one feels a little more intuitive, I guess,
Mhm.
but our source highlights some aspects that I hadn't fully considered before.
Okay.
So obviously a headwind on takeoff and landing is going to shorten the ground roll,
Right.
while a tailwind is going to lengthen it, as Figure 5.2 illustrates.
Yeah, makes sense.
But the material also mentions this need for good crosswind techniques
Mm-hmm.
during launch and landing
Right.
to keep the glider, aligned with the runway.
Yeah.
What I found particularly interesting was this concept of wind gradient,
Oh, yeah.
where wind speed can increase as you go up in altitude
It does.
because there's less friction from the ground slowing it down.
Right.
So you can imagine this increasing wind with altitude is almost like an invisible speed bump during launch, right? What feels manageable on the ground can become too much as you climb.
That's a great way to put it. Yeah, I hadn't thought of it like that.
Yeah, Figure 5.3 really shows that. So during a ground launch, if that wind speed picks up significantly as the glider's lifting off, you could unintentionally exceed the maximum safe launch speed, even if your ground speed initially was fine.
Yeah, you don't want to be caught out by that.
Definitely not. Now, once you're cruising along in flight,
Mm-hmm.
the impact of wind on ground speed is pretty direct.
Right.
Headwind slows you down,
Yeah.
tailwind speeds you up.
Yeah.
And they give this example of a 60-knot true airspeed
Okay.
directly into a 25-knot headwind, which gives you a ground speed of 35 knots.
Wow.
It's a big difference, especially for those cross-country flights.
Oh, yeah. That's a huge impact.
And for those of you flying self-launching gliders with engines, our source makes this point that wind does affect your range.
Okay.
It's going to reduce how far you can go against a headwind and increase it with a tailwind.
Makes sense.
But it doesn't change your flight duration, which is limited by fuel, obviously.
Right.
And they wisely direct us to the GFMPOH for recommended airspeeds to use in different wind conditions.
Always good advice. Always check the manual.
Always. So when you're trying to fly in a straight line
Mm-hmm.
over the ground, but you've got a crosswind, our text explains this idea of using a wind correction angle.
Right.
You're basically pointing the glider slightly into the wind
Okay.
to counteract being blown sideways, as shown in Figure 5.4.
Yeah.
It's also worth remembering that any crosswind, it's going to have a component that acts as either a headwind or tailwind,
Mm.
affecting your overall speed over the ground.
Right.
Okay, so approaching and landing when it's windy, Seems like it takes some real finesse.
Yeah, for sure.
A headwind on final approach means you're going to lose more altitude for the same distance over the ground,
Makes sense.
making your approach angle look steeper.
Okay.
And our source mentions techniques like flying a slightly closer base leg and delaying the use of spoilers or air brakes
Right.
while carrying a little extra airspeed to manage that.
Smart.
And conversely, if you've got a tailwind on approach, the
Yeah.
opposite happens. The approach angle looks shallower,
Okay.
and you might need to use more spoilers, dive brakes,
Right.
maybe even slip
Yeah.
if the glider's manual allows that.
Yeah, good point.
Now, experienced pilots will often aim to touch down a little bit beyond the runway threshold
Mm-hmm.
as a safety margin
Yeah, that's a good idea.
against sudden wind changes near the ground.
Yeah, especially with those wind gradients we were talking about.
Exactly. Now, talking about those wind changes, our document actually mentions the potential for a sudden loss of airspeed on final approach if you've been flying into a headwind,
Right.
and it suddenly weakens or disappears as you get closer to the ground.
Yeah, yeah.
If you're not ready for that, you could end up landing short.
Definitely a scary thought.
Yeah. On the other hand, if you're landing with a tailwind, you're going to have a longer rollout,
Mm-hmm.
and you might even see a brief increase in airspeed as that tailwind goes away at ground level.
Okay. Now, one thing to really watch out for is the effect of a strong wind shear gradient during low altitude turns.
Okay.
Especially on final
Mhm.
figure 5-6 in our material, actually illustrates how a big difference in wind speed across the span of your wings
Right.
can create unequal lift,
Yeah.
causing a roll
Wow.
that your ailerons might not be able to overcome.
That's no good.
No, no. So limiting your bank angle if you suspect strong wind shear is really good advice.
Okay, that's a good overview of the sometimes tricky world of wind.
It is, it is.
So let's move on to the impact of weight.
Yeah,
Seems like a heavier glider is going to have some pretty direct effects on how it performs.
it does. For starters, it's going to take longer to accelerate to takeoff speed.
Okay.
And the tow plane's going to really notice that extra weight trying to get you up in the air. Figure 5-7 shows that pretty clearly.
Right, right.
And the speed at which your glider stalls when it loses lift isn't a fixed number.
Right.
It actually increases as the glider gets heavier, or if you experience higher load factors, like when you're turning.
Okay.
You know, our source gives a very clear example, a 540-pound glider that stalls at 40 knots.
Mm-hmm.
Well, if you add 300 pounds of water ballast, that stall speed goes up to around 50 knots.
That's significant.
It is, and it's just something to be aware of. You know, adding ballast is kind of like giving your glider a shot of adrenaline when it comes to speeds.
Right.
But you have to remember, every extra pound makes it a little more reluctant to get off the ground.
Right, yeah.
And a little more eager to stall if you get too slow.
Okay. And the speed at which the glider sinks, the slowest, that minimum sink airspeed,
Yeah,
that also increases with weight, right?
it does.
And heavier gliders might need to fly at higher airspeeds when circling in thermals to be efficient.
Mm-hmm.
But that means they're going to be making wider, less tight circles,
Right.
which could lead to them drifting out of the strongest part of the lift, as shown in Figure 5.8.
Yeah, those are all trade-offs
Mhm.
you have to be aware of.
Yeah. So the best glide speed, the one that gives you the best lift-to-drag ratio,
Have the best LD.
that also increases with weight, as we see in Figure 5.9.
It does. So while a heavier glider will sink faster overall,
Right.
it can still cover the same horizontal distance
Okay.
as a lighter glider with the same glide ratio,
Okay.
but it needs to do so at a higher speed.
Now, this is interesting. Our source points out that this extra weight can actually be an advantage when you're flying faster between thermals,
Okay.
especially if you're flying through sinking air. The ability to fly faster and still maintain that good glide ratio can more than make up for that slightly slower climb rate once you find lift.
That's really interesting, that trade-off there.
Yeah, it's all about strategy, right?
It is.
And this is where this idea of water ballast comes in.
Mm-hmm.
Essentially, extra weight, usually water
Right.
carried in tanks within the wings
Okay.
that pilots can add to specifically enhance performance during those faster cruising legs.
Interesting.
And the really clever part is this water ballast can usually be dumped
Okay.
before you enter the landing pattern,
Right.
allowing you to reduce the weight for a more normal approach when landing.
I like that idea of being able to, kind of tailor the weight of your glider to the conditions.
Yeah, that adaptability is key.
It is.
Which brings us to flight manuals and those all-important placards.
Yeah.
Our source emphasizes that the Glider Flight Manual, or Pilot's Operating Handbook, GFMPOH, is your absolute go-to resource for safe operation.
It is. It's the Bible for your specific glider.
Exactly. Packed with essential information from descriptions of all the glider's components and assembly instructions to critical data on weight and balance, systems descriptions, specific performance figures, and of course all those operating limitations. And then we have the placards. These are those bits of information displayed right there in the cockpit.
Right, right.
And Figure 510 gives us some good examples of what these placards might include. Things like engine RPM limits for self-launchers,
Okay.
clear instructions on how to use that emergency canopy jettison system, which hopefully you never have to use,
Yeah, hopefully not.
the approved minimum and maximum pilot weights,
Right.
any prohibited maneuvers, and crucially, those key airspeeds, like the stall speed and VNE, which is velocity, never exceed.
So important to know those.
Absolutely. Those placards are there for immediate reference and definitely not to be ignored.
Yeah, you really have to pay attention to them.
Now, getting a little deeper into performance information, our source reminds us that the GFMPIOH will list all those specific airspeeds we mentioned earlier, the stall speed, minimum sink speed, the speed for best LD,
Right.
maneuvering speed, rough airspeed, max speeds for aerotow and ground launch, VNE, and even VFE for gliders with flaps.
Okay.
And for those flying self-launching gliders, you'll also find data on powered operations, like the best rate of climb, engine limits, fuel consumption, endurance, and recommended cruise speeds.
It's all there.
It really is. It's all there in the manual.
Yeah, it comes down to, knowing your numbers.
Right.
Each glider has its own unique set of airspeeds that define its safe and most efficient operating envelope.
Okay. Now, this next bit is particularly insightful, I think. Glider polars.
Oh, yeah.
Our source describes these as graphical representations provided by the manufacturer
Right.
that show how quickly the glider will sink through the air at different airspeeds,
Right.
like in Figure 511.
It's almost like a unique fingerprint for each specific glider model.
That's a great analogy.
Yeah.
So on this graph, the vertical axis is showing you the rate of descent, and the horizontal axis is the airspeed.
Right.
And what's important is that each design has its own unique polar curve. And even little things like the smoothness of the surfaces, how well the control surfaces are sealed,
Ow.
can affect it. Our source even mentions the impact of bugs on the leading edge.
Oh, wow. That's amazing.
So looking at these polar curves, you can actually identify key performance speeds.
Right.
The lowest point on the curve is that minimum sink airspeed. So that's the speed where you're losing the least altitude over time,
Okay.
which is crucial for staying up in a weak lift.
Yeah.
And then if you imagine drawing a line from the bottom left corner of the graph, the origin, and that line just touches the curve at a single point. That point is your best glide speed.
Okay.
That's the speed that gives you the greatest distance for every foot of altitude you lose.
In still air?
Yeah. The source gives this great example. A minimum sink rate of 1.9 knots at 40 knots,
Okay.
and a best LD speed of 50 knots with a sink rate of 2.1 knots,
Right.
giving you a glide ratio of 24:1.
Which means for every 24 feet forward, you only lose 1 foot of altitude.
Exactly. That glide ratio is a crucial performance metric.
It is.
Now, the polar curve can also tell you more when you factor in wind.
Okay, how so?
Figure 512 shows how you can determine the best speed to fly when you have a headwind. Basically, you shift the origin of the graph to the right by the speed of the headwind
Right.
and draw a new tangent line. Where that new line touches the polar is your optimal airspeed.
I see.
A good rule of thumb is to add about half the headwind component to your zero wind best LD speed.
That's a good tip.
And then with a tailwind, the best speed to fly is generally somewhere between your minimum sink speed and your best LD speed.
Okay.
But you never want to fly slower than minimum sink. You'll just descend faster without getting much distance.
Right. That makes sense.
What about when you encounter air that's generally sinking?
Yeah, that's tricky.
Figure 513 actually shows how you can adjust your speed to fly more efficiently by shifting the origin of that polar curve upwards by the sink rate of the air.
Okay.
Now, your variometer in the glider is going to show the total sink rate,
Right.
both the rate at which the air is moving down and the glider's inherent sink rate.
Got it.
So it's a lot of information packed into these polars.
Yes.
And our source also touches on how things like adding ballast, using different flap settings, and even wingtip extensions can change the shape of that curve.
Oh, that's interesting. So you can really fine-tune things.
Yeah, like in Figure 514, Figure 515, and Figure 516.
Mm-hmm.
So adding water ballast generally increases both the minimum sink rate
Okay.
and the airspeed at which that minimum sink occurs,
Right.
which can make it tougher to stay up in very weak lift.
Okay.
but it reduces the glider's sink rate at higher airspeeds.
Okay,
So the best glide ratio might remain the same, but it's achieved at a higher speed.
got it.
Now, using negative flap settings can actually be beneficial at higher cruise speeds by reducing that sink rate.
Okay.
And wingtip extensions can often provide a performance advantage across the whole speed range,
Wow.
potentially improving both low-speed and high-speed performance.
So each of those modifications has its own set of pluses and minuses.
Exactly.
You're really playing with the characteristics of the glider.
Yeah, it's all about understanding those trade-offs.
It is. It is.
Now, all this talk about performance leads us to limitations.
Yeah.
And our source emphasizes that manufacturers provide these limitations for safety.
Of course. Yeah.
So the glider's VG diagram, like the one in Figure 517, visually shows the limiting airspeeds
Mm-hmm.
and maximum load factors, or G-forces,
Right.
that it's designed to withstand.
Right.
You can think of G-force as how many times your body weight you're feeling due to acceleration.
Mm.
So higher G-load means more stress on the structure.
It's crucial to know those limits.
It really is.
Respect them.
Yeah. So the VG diagram basically defines that safe operational envelope.
Right.
Condition 1 on the diagram is that maximum speed you can safely use full of elevator without risking structural damage.
Okay.
At lower speeds in this range, you'll stall the wing before you can exceed the limits.
Right.
But at higher speeds, you could overstress the glider.
Got it.
Condition 2 is the equivalent for full-down elevator.
Okay.
Now, our source raises this important point about encountering those vertical gusts when you're cruising at higher speeds.
Oh, yeah.
Those sudden up or down movements can really increase that G-load
Mm-hmm.
and also store elastic energy in the wings,
Right.
which can sometimes lead to pilot-induced oscillations, or PIOs,
Right.
which are basically unintentional and potentially dangerous cycles of pitch or roll.
Yeah, you don't want to get into those.
The advice is clear. If you encounter turbulence, reduce airspeed and brace your arms to avoid making those large control inputs.
Smoothness is key,
Exactly.
especially in turbulence.
And finally, we come to weight and balance.
Yeah, this is a big one.
Our source rightly emphasizes this as fundamental to safe flight.
It is.
Overloading the glider or having it loaded improperly can have really serious consequences for how it
You
handled.
can.
And of course, the GFMPOH is your primary source for weight and balance information.
It is. Always check the manual.
Right. And it's not a one-time check.
Right.
Any modifications made to the glider that affect weight or center of gravity
Mm-hmm.
have to be documented by qualified AMTs.
Right. The aviation maintenance technicians.
Exactly.
They're the ones who keep everything safe and legal.
So this concept of center of gravity, or CG,
Yeah,
is absolutely central to how the glider balances in pitch.
it is.
So for it to be stable in pitch, that CG needs to be forward of the center of lift of the wing,
Okay.
and the horizontal stabilizer on the tail provides a downward force to balance the glider around that point.
Right.
Our source explains this idea of positive stability,
Mm-hmm.
which is that tendency of the glider to return to its previous pitch attitude after it's disturbed.
Okay, that makes sense.
But things can go wrong if that CG is outside the limits. If it's too far forward, it can make it really hard to raise the nose on takeoff.
Right.
You might find yourself needing a lot of back pressure on the stick just to maintain pitch.
Okay.
And there's also the potential for a tail stall at low air speeds,
Yeah, that can be dangerous.
which could lead to a sudden nose-down pitch.
Right.
And maybe most critically, a forward CG can mean you don't have enough elevator authority during landing,
Oh, wow.
which increases the risk of a hard landing.
That's something you definitely want to avoid.
Absolutely. Common causes of this are exceeding the maximum pilot weight or carrying too much ballast in the front.
Makes sense.
Now, if the CG is too far aft,
Mm-hmm.
we call that tail heavy.
Right.
And you might find that pitch control is very difficult or even impossible.
Yeah, that's not good.
So some causes of an aft CG could be the pilot being lighter than the minimum weight
Okay.
without enough ballast in the front, forgetting to remove a tailwheel dolly,
Mm-hmm.
having a heavy or unapproved tailwheel assembly,
Right.
or even just debris in the rear fuselage.
Interesting.
Our source gives a helpful example of a weight and balance problem
Okay.
using both a graphic envelope, like in Figure 518,
Mm-hmm.
and a computational method, shown in Figure 519.
Okay.
The graphic shows the acceptable weight ranges for the pilots in the front and rear seats,
Right.
and the computational method involves taking the weight of each component,
Okay.
the glider itself, the pilot's baggage, ballast,
Mm-hmm.
and multiplying that by its arm, which is the distance from a reference point on the glider, called the datum.
Right.
That gives you the moment for each item.
Okay.
You add up all the weights
Mm-hmm.
and all the moments, and then divide the total moment by the total weight to get the CG position.
Got it.
And it's super important to then compare both that total weight and CG position to the limits in the POH.
Absolutely, yeah. Safety first.
Always. Okay, let's talk about ballast.
Yeah.
Our source defines it as any non-structural weight added to the glider.
Okay.
And it serves two main purposes, trim and performance.
Makes sense.
Trim ballast, which is often removable lead weights, is used to adjust the CG
Right.
to keep it within those safe limits. Expert speaker.